So in the past, you've used mass percent data to calculate and determine empirical formulas. Here we're going to talk about a new technique, combustion analysis. And it uses the mass of carbon dioxide and water produced by a combustion reaction to determine an empirical formula as well. Really cool when you start thinking about the logistics of it all. The calculation is kind of involved. We're going to go through that step by step. But logistically in the lab, it's a pretty straightforward technique that takes advantage of the law of conservation of mass. As you saw in the combustion reactions, the equation is super predictable. So the scientists will burn some kind of hydrocarbon fuel, and then they'll collect the carbon dioxide and water. They have to collect all of it. And then they can separate the carbon dioxide gas from the water by lowering the temperature a little bit and causing the water to condense. In this problem, we're told that they collected 14.08 grams of carbon dioxide. I'm going to use the molar mass of carbon dioxide to convert that value to moles of carbon dioxide. After that, I need to consider the relationship between the moles of carbon dioxide that are produced by the combustion reaction and the moles of carbon in my fuel source. And you may have noticed as we were balancing these equations that for every carbon in your fuel source, you had 1 molar equivalent of carbon dioxide. So it's a 1-to-1 ratio between carbon dioxide and carbon in the fuel source. The other thing that reminds me about that is the formula of carbon dioxide. So in the formula for carbon dioxide, there's 1 carbon. So I'm going to use that to get rid of moles of carbon dioxide. So in my denominator, I'm going to say 1 mole of CO2. And in my numerator, 1 mole of CO2 contains 1 mole of carbon. All right, after you do the math, you're going to get 0.31993 moles of carbon. We have to do a similar analysis on the mass of the water that was produced. We were told it was 4.32 grams of water. My first conversion factor is going to use the molar mass of water. My second conversion factor, again, thinking about how the equations were balanced or thinking about the formula for water itself. Every time we have 1 mole of H2O, we have 2 moles of hydrogen. As with all our stoichiometry dimensional analysis problems, we always want to check how things are canceling. So grams of water will cancel grams of water, moles of water, moles of water. And that results in 0.47947 moles of hydrogen. Our goal with the next couple of steps is to determine the mass of oxygen and ultimately the moles of oxygen in our sample. So if you have a problem where you know for certain that there is no oxygen, you were told that, then you can skip steps 3, 4, and 5, and 6 as well, and just jump right to step 7 where you start dividing by the lowest molar ratio. However, the tartaric acid does have oxygen, and in all of the examples with oxygen, it's a little bit difficult to analyze because there's that excess oxygen that's picked up when the sample's burning. So with carbon and hydrogen, all of the carbon and all of the hydrogen comes from the sample itself. But not all of the oxygen comes from the sample, right? Because oxygen gas is also a reactant. So we have to be a little bit clever about our analysis. We still are going to use law of conservation of mass though. We're going to take the moles of carbon and the moles of hydrogen that we just calculated and convert them to mass of carbon and mass of hydrogen. So for carbon, I'm going to use its molar mass, 12.01 grams of carbon. And that gives me 3.8423 grams of carbon. I'll also use the molar mass of hydrogen here to figure out how many grams of hydrogen we're dealing with. And we're looking at 0.48426 grams of hydrogen. Really quickly, sometimes students, when I'm doing this lecture, are kind of bothered by the fact that I stopped paying attention to sig figs. At the end of the day, you're gonna be writing a formula, so I would keep the sig figs, keep as many of the values as you can in the calculator, but a little bit of rounding here or there is not going to hurt. Just don't round too much that you lose the ratio that's going to become apparent soon enough. But you don't have to stress about sig figs with these problems. That's the nice part about them. So now that we know the mass of carbon and the mass of hydrogen, we were told that the sample before they burnt it was 12.01 grams. So if the whole thing was 12.01 grams and it had carbon, hydrogen, oxygen, we take away the mass of the carbon. We take away the mass of the hydrogen. And we're just going to be left with the mass of the oxygen. In the next step, I took the mass of oxygen that we obtained by subtracting, and then I divided that by its atomic mass. And that gave me the moles of oxygen in the sample. Then I grabbed all of the mole values, and it's really critical that we grab the mole values and not the masses. So I grabbed all of the mole values, and I'm going to look them over and identify my lowest mole value, which happens to be carbon here. And I want to divide all three mole values by the lowest value. This is going to help us establish the mole-to-mole ratio. All right, so after I did that, I got C1, because I divided carbon by itself. Hydrogen came out to be like 1.48, something like that. When you get those numbers that are really close to maybe the tens place or the ones place, you do want to round. So a little bit of rounding is okay. So I'm going to write this one as H1.5. I don't want to round all the way up to 2 or all the way down to 1, but it's close enough to 1.5. And the same thing with oxygen. Now, we've never seen a formula that has decimals in it. That's not a thing. So at this point, we need to multiply this equation, this formula, by, usually it's a pretty small number. In this case, it's going to be 2. And that's going to give us our whole number ratio. So multiply to obtain a whole number ratio. After multiplying each of the mole-to-mole ratios by 2, I get C2H3O3, and that's going to be our empirical formula for the tartaric acid. The next step when we need to determine the empirical formula is to calculate what I like to call the empirical mass. It's a term I made up, so that's why I put it in quotes. We're going to take that empirical formula that we just calculated and use the subscripts, same way you calculate any kind of mass. And when I did that for the tartaric acid sample, I got 75.05 grams for my empirical mass. After that, we need to establish the ratio between the molecular mass and the empirical mass. And that's going to give us insight into the relationship between the ratio between the molecular formula and the empirical formula. So in order to do that, I'm going to look up the molecular mass that they gave me. So they said it was 150.09 grams. That's the molecular mass. And I'm going to divide by my empirical mass. So divided by 75.05 grams. And ignoring what's going on in the hundreds place, 150 divided by 75, I can see that the ratio is 2 to 1. So that means that our molecular formula is going to be twice as big as our empirical formula. So I'm going to take my empirical formula, C2H3O3, and multiply it by 2. That gives me C4H6O6. And we can check our work. If we calculate the molecular mass of this compound, this formula, then indeed it gives us the 150. And that's how one of the ways we know that we successfully determined the molecular formula of the tartaric acid.